Buongiorno a tutti, anche da parte mia e dall'intero comitato tecnico-scientifico del JTF. È con grande piacere che annunciamo l'avvio della 16ª edizione del Jewelry Technology Forum e a me spetta il compito di moderare la prima parte, cioè della giornata, la mattina. Al termine di ogni relazione ci sarà la possibilità da parte dei presenti, avete il format nella vostra cartellina, di formulare uno o più quesiti ai relatori che risponderanno al termine della loro relazione. Ci sarà una persona che raccoglierà il format all'interno della sala. Raccomando agli speaker, come al solito, di attenersi al tempo loro dedicato per la relazione e con grande piacere mi invito il primo relatore, storico relatore del JTF, profondo conoscitore del nostro settore, è Chris Corti. Chris Corti ha maturato 40 anni di esperienza nell'industria dei metalli preziosi presso Johnson Matthey PLC e World Council, prima di costituire la propria società di consulenza nel 2009, la Core Gold Technology. Ha un PhD di metallurgia all'Università del Surrey nel Regno Unito e prima di dedicarsi al settore dei metalli preziosi ha lavorato nel settore energetico in Gran Bretagna e in Svizzera. Da lungo tempo è relatore di presentazioni sulle tematiche della gioielleria in occasione del simposio di Santa Fe e del Jewelry Technology Forum. La sua relazione ha titolo L'importanza del grano cristallino e del suo controllo in gioielleria. Il controllo del grano cristallino nella produzione di gioielleria è estremamente importante, dato che da questa caratteristica dipendono molte proprietà di una lega dal punto di vista meccanico, chimico e fisico. Queste ultime influenzano il processo di produzione e le prestazioni finali del gioiello durante l'uso. La presentazione del dottor Corti si sofferma su quali metodi si possono usare per controllare il grano cristallino, sia mediante aspetti processuali, sia mediante l'utilizzo di elementi presenti in lega. Prego, Chris.
Good morning, everybody. Thank you for that kind introduction. I would just like to mention that when I first came here in 2004, my hair was black. I'm going to talk today about grain size and its control in jewellery alloys and hopefully get across the message, why is it important? See if I can work this machine. There we are. I think the first point I'd like to make is if you're working with jewellery and you're manufacturing jewellery, you need to understand the importance of grain size, grains or crystals in the alloy. And you need to understand, for example, that the way you alloy the metal, the way you process it will influence the microstructure of the material that you've produced and the properties. And these are all interrelated. You change one, you change the other. So if you change the alloy composition, you change the properties, you change the microstructure. And I think that's the first point. The second point is, for those of you who are not metallurgists and have not had the excitement of going through university, most metals that we deal with in this world are what we call polycrystalline. They're made up of crystals of the alloy, and there are many crystals in the volume. And the crystals all have different orientations in space, so when they come together and touch the adjacent crystal, you don't get a good match of the atoms, and as you can see on the bottom slide there, you get gaps and spaces at the grain boundary, and this can be deleterious to your alloy because this is where the bad impurities will collect. This is where bad second phases can precipitate and collect and give you all sorts of problems like cracking and embrittlement. The focus of my talk is going to be on the microstructure of jewellery alloys, and particularly grain size and shape. And I'm going to try and answer the question, how can we influence the grain structure, the grain size, by casting our alloy, by mechanical working, and by annealing? And why are they important? And I give on the slide two examples. On the left side, you can see a microstructure of the cross-section of a ring shank, and you can see that the crystal grains go right across from one side to the other. This is not a good metallurgical structure, and you're likely to get the ring cracking and breaking. On the right side is another microstructure of a palladium alloy, which has been laser welded, and you can see areas on the left-hand side of the picture where the structure is quite coarse. There's large grains, and you can also see some structure within those grains. It's an as-cast structure because you melted the alloy at that point when you welded it. And these are the sorts of things you need to be aware of when you're using processes. What does it do to my material? So I think I've already made this point. We as metallurgists in the trade, we pay attention to the grain size, the crystal size of the alloy. And we talk about large grain sizes or coarse grain sizes or fine or small grain sizes. And what do we mean by those terms? Well, if you're talking about large grain sizes, we're generally talking about grain sizes of 1 millimetre or larger. And if we're talking about fine grain sizes, we're talking about sub-millimetre size, say typically 500 or less microns. And you will occasionally come across in the trade the use of a number for grain size, the ASTM grain size. I'm not going to get into the details of what the number means in terms of grain size, but generally the higher the number, the smaller is the grain size. So why is control of grain size important? And as I've emphasised, it's the relationship between grains and grain boundaries that influence the mechanical deformation processes in metals. And as we've said, grain boundaries are where the atoms sitting on the crystal lattice of adjacent grains do not match perfectly together. They create a region of imperfect crystal, preferred sites for deleterious impurities and second phases. And we will see some examples later. So I need to get into some basics so you begin to understand why these things are important. And first of all, when we deform a metal, whether it's a precious metal alloy for jewellery or a steel for making cars or a nickel alloy for aircraft engines, they all obey the same rules. Under the imposed load or stress, we change the shape of our material, we roll it, we hammer it, whatever we do. And when we change the shape, the crystals within have to also change their shape to accommodate that external shape change. And that occurs by complex patterns of slit of planes of atoms over each other. But the outcome that's important to understand is the finer your grain size, the stronger or harder it is. And that's covered by a relationship that we call the Hall-Petch relationship. The yield stress, the stress at which the metal starts to deform, is proportional to the inverse of the square of the grain size. So the finer the grain size, the stronger, the harder your material will be. So that's one of the things that we would like to achieve, I think, when we're making jewellery. We want a good, strong alloy. This is a slide which, if you've never been involved before, just tries to illustrate how planes slide over each other, and it's done through a defect in the crystal structure that we call dislocations. I'm not going to get into the details of it, but I show you some slides there where you can see on the top right-hand side slit bands on the surface of the copper from the deformation. And if you get into an electron microscope at very high magnification, you can actually see these defects, these dislocations, and you can see them move when you apply stress. But I'm sure we don't want to get into that. So, why is a fine grain size important? I've just mentioned it's stronger, it's harder, it's also more ductile, it's less prone to cracking, it's less prone to impurity embrittlement. If you've got impurities sitting on grain boundaries and you've got a fine grain size, you've got a much bigger grain boundary surface area to spread out those impurities, and therefore it's less likely to be damaging. And of course, if you work material and make jewellery, you will know that if you've got a coarse grain size, you will get an orange peel surface as you deform your material. It's a rumpled surface that isn't so nice, and that would therefore require a lot more polishing to get up to the condition. And the other thing, of course, is if you've got a finer grain size, it'll actually be easier to polish. So, all good reasons. Now, I'm just going to diverge for a little bit and talk about deformation at high temperatures, which is not something we're generally concerned with in the jewellery industry, but I think one needs to have a picture to set it into context. If we're deforming materials at high temperature, for example, the blades in a jet engine, they're operating at high temperature. We have different deformation mechanisms. We have a mechanism of creep and we have a mechanism of fatigue. Creep is the slow deformation of a material under a steady imposed load, and fatigue is a failure due to alternating imposed loads. And at higher temperatures, the grain boundaries in the structure are weaker than the crystals themselves. Grains will slide over each other in creep. And so we generally want to reduce the grain boundary surface area if we're operating materials at high temperature. We prefer a large grain size, totally the opposite of what we want in jewellery. And the ultimate example of that is in the turbine blades, in the jet engines that fly you around the world, and there they have moved to making their turbine blades as single crystals with no grain boundaries there at all to remove that deformation mechanism. And I just show there an example. So on the left-hand side, we've got a normal random polycrystalline structure, and you can see in the picture there grains, and then they moved to what we call directional solidification. So we've got a lot of grains, but they're all in the direction of stress. And then finally, on the right-hand side, a single crystal turbine blade. We don't need to worry about that in jewellery, but I just thought you'd just like to be aware that in all engineering disciplines, we are manipulating the structure, grain size, for good reasons. I'm just going to talk about another mechanism that can happen at elevated temperatures. If you've got a very fine grain size and a stable grain size, and you gently deform it at high temperatures under low stresses and slow strain rates, you get a phenomenon known as superplasticity. You can achieve very high deformations of several 100%, and this is a technique that is exploited for net-shaped components in the aerospace industry. The very large fan blades at the front of your Boeing 747 are made, if it's a Rolls-Royce engine, by superplastic forming. Titanium floor patterns and things are also made by superplastic forming. Now, interestingly, in the precious metal field, we haven't yet exploited superplasticity as a way of producing shapes, but there has been some work done at Johnson Matthey many years ago that shows that sterling silver can be deformed superplastically. So maybe this is something one day that we might find a role for in our jewellery manufacture. And I just thought you need a few pictures to get over my boring talk. So superplasticity is very much like making fondue. You know, you get nice long streaks of cheese and things. So that's the end of my digression. The other thing I just wanted to say a little bit about is is I'm showing you pictures of structures. How do we get those structures? We look down a microscope and the techniques known as metallography. We usually look down an optical microscope where we're using light. And to do that, we need a sample with a flat, polished surface because the optical microscope has got a very limited depth of focus. And then we then treat the surface with an acid or some chemical to etch it to reveal the microstructure. And if we do it properly, we can see the grain boundaries and we can see second phases and other aspects of the structure that you can't see just on a polished surface. If we need to get greater magnification or we want to look for a larger depth of focus, if we're looking at a fracture surface where we haven't got a flat polished surface, then we'll go to the use of a scanning electron microscope. And under the scanning electron microscope, you will see phase contrast because heavy elements reflect differently to the lighter elements, and so you can see different phases just by atomic number contrast. But we don't want to get into too much detail there. Again, I just show you here some pictures. On the left-hand side, we've got some as-cast structures. The top one's 18 karat gold, the bottom one's a 950 palladium, but you can see similarities. There's a structure within the grains, whereas if we look on the right-hand side, we've got an annealed gold alloy. We see the crystal structure looks a little bit different, and then on the bottom some fine silver where I'm not sure what the magnification is, but this looks to be quite a large, coarse-grained material. So how do we control grain size? So I'm going to talk about that. I'm going to talk about casting and then about working and then about annealing as how we might control our grain size. So why do we cast metals? We cast it for two reasons. One, to get alloys of the desired composition. We put a bit of gold with some silver, with some copper and maybe one or two other things, zinc or nickel or whatever it is, and we melt them together to get an homogeneous alloy, and we then cast those to get specific shapes of metal. We might be casting by the lost wax casting process to get specific net shapes, the ring or whatever it is that we want to make. Or on a larger scale, we may be casting ingots to get a block of metal that we can then further work to get the shapes and materials that we need. And of course, we've also got things like continuous casting, which gets us closer to a shape that we want to use, but maybe not the final shape. The important thing is that these mechanical processing of these materials will break down any coarse, non-uniform structures that we get from casting and give us a more refined structure that we would prefer, and that includes the grain size. So let's talk about how we can control grain size in casting. And I show you an example there of a cross-section of a silver ingot. And I think what's important is you can see that it's not a homogeneous grain size. On the sides of the ingot, we've got long grains coming in towards the centre, and then in the middle we've got equal-shaped grains in the middle. And this is the way we've cast and cooled the ingot will control that grain size. So that's going to depend on the size of the ingot. The larger the ingot, the coarser your grains are going to be. And it's also going to depend on the thermal conductivity of the mould material. If we're casting into an iron or copper mould, we've got rapid heat extraction. If we're casting, as an investment casting, into a ceramic mould, we've got a slower rate of cooling, and that will affect the microstructure. Just again, a reminder, pure metals solidify at a fixed temperature, but alloys generally will solidify over a temperature range between the liquidus and the solidus lines. And I've got a gold-silver phase diagram there, just showing you the top line is the liquidus, the bottom line is the solidus. And the size of the gap between the liquidus and the solidus will also influence the cast structure that we end up with. So what happens when we cool a molten metal down in a mould? We get small clusters of atoms coming together and forming a nucleus. And they would generally happen at preferred sites. It might be on the mould walls, it might be on inclusions that are floating in the liquid metal, but it can also just generally occur randomly within the melt. And as we cool more and more atoms will coalesce on the nucleus in a structured way that forms the crystal structure of the alloy that we're dealing with. And for the precious metals, we're generally talking about a crystal structure that's called the face-centered cubic structure. That's a fairly ductile structure, one that we like. So these clusters of atoms are our embryonic crystals or grains that will make up the solid alloy. And we're just going to have a little bit closer look at what impact that has on grain size. A fast cooling rate results in the formation of more nuclei in our melt, and each of those nuclei will develop into a crystal or a grain. So you end up with a finer grain size. If you have a slow cooling rate, you get less nuclei forming in the melt, and so you get resultant larger grain size. And if you've got insoluble particles floating about in your melt, these will also act to nucleate and therefore act as grain refiners. They help to create a finer grain size. And we will talk a little later about grain refining, particularly in carat golds. Grain refiners promote enhanced nucleation in the melt. So we've talked about this. Nuclei grow by adding more atoms from the liquid. They grow in preferred crystal directions, extending from the cube faces of your crystal, and they branch out as it goes, a bit like a tree. It's a tree-like structure that we call a dendrite, and the orientation of each dendrite in the melt will vary depending on how it sits, and they grow and grow until they collide with each other, and then they fill in the spaces until you've got a solid alloy, and we see that schematically in the three pictures at the bottom there. And here's a picture of a dendrite as viewed through a shrinkage cavity in a casting, and this is of a platinum alloy, even though it's nice and gold coloured. And then schematically on the top right there, the dendrite. And just bear that shape in mind when we look at cast structures. And here we've got three cast structures, two of gold, one of palladium. You can see this structure. You can see that dendrite pattern in the microstructure. And the reason you get that pattern is because the first metal that starts to solidify is of a different composition to the last metal that solidifies. You've got a concentration gradient from the centre to the outside of your grain. There are chemical differences. We call that in the trade coring. But what it does illustrate, because you can see the direction each of the dendrites in the grain is pointing, that they all have a different orientation in space. So let's get into the solidification and how we change grain size. When we pour molten metal into an ingot mould, the ingot mould is clearly cooler than the molten metal, and so you start to solidify on the faces of the mould, and it starts to solidify in towards the centre of your mould cavity. And as you can see in the schematic, you can see dendrites growing in towards the centre of the molten metal. If we use a cold metal mould, as we do in ingot casting, the rate of heat removal is rapid. We get initially a thin chill layer of fine grains forming on the outside because we have a very high nucleation rate. And then we see these longer columnar grains growing in towards the centre, as we see in the sketch. Whoops. Again, we've already seen this picture, just a picture of a 950 palladium alloy. You can see the cast structure there, the segregation of the dendritic structure. Now, if we cast our molten metals at a high temperature, a lot of superheat, the columnar grains will grow until they meet in the centre of the ingot. This is not a good structure. Any impurities we've got in our alloy will tend to concentrate in the centre because that's where the last piece of metal solidifies. And when you take that ingot and start to roll it down to change its shape, you may find it just splits apart, alligatoring, as we call it in the trade. And those of you that make alloys may have come across this problem on the odd occasion. So we don't want this structure. So we would prefer, if we can keep our casting temperature, the temperature of the metal when we pour it into the mould, closer to the solidification temperature. And we find that as we cool, nucleation starts at the mould walls, it starts to grow inwards, we start to get some columnar grain formation, but then we get general nucleation within the molten metal, and we end up, as you can see in the sketch, with a band of smaller columnar grains, but equiax shaped grains in the centre. This is much better, much preferred structure if we're going to cast ingots for further working. So that's one way we can control our grain size and grain shape, just by simply the way we just cast our metal. Now, if we're casting in a ceramic mould, as we do in investment casting, we have a slow cooling rate, and so we get a lot of nucleation in the general structure. We don't get these columnar grains growing in from the centre, in from the edge to the centre, and this is a good structure. So generally in investment casting, we end up with a good microstructure of equiax grains of a reasonable size. So we've got our cast structure. We then normally, in most jewellery manufacturing processes, unless we're making rings, say, for example, by casting, we then need to do further work to change the shape, to get to the materials, the sheets, the wires, the rods that we need to make our jewellery. Our cast structure is probably not the optimum structure for what we would like. We've got chemical segregation, the coring, we've got coarse structures, and this will tend to give us poorer mechanical properties, poorer corrosion properties. So we work in the material to change the physical shape, but also to refine the microstructure. We reduce the segregation, we refine any second phase particles to finer, more uniform particles, and we're generally improving the mechanical properties. We can best achieve this by hot working our alloy, so hot forging, hot rolling. It refines the microstructure, but we're getting annealing happening while we're working the material, and we end up with a material that's in the soft annealed condition. The metal is recrystallizing, and we'll come on to this in a moment, during the deformation. Very often we prefer, for other reasons, to cold work our material, particularly after we've hot worked it. This imparts deformation. We work harden the material, it strengthens the material, as well as refining the microstructure. But if we do that, we know we cannot just keep doing that, it'll crack. We need to anneal it at some stage to get back to a soft ductile condition, and we do that by annealing. And cold working, as we said, results in a shape change. The grains must change their shape, but they also become full of dislocations, these defects in the crystal, which makes it harder to work the material. It's work hardened, and as we've said, this occurs by sliding of crystal planes over each other. And the schematic on the left-hand side shows how the grains are changing shape as we reduce our material by cold rolling. If we overwork it, we'll end up cracking and breaking our material. So we have to anneal. Just here, illustrate two examples. The top left-hand picture shows a washer that's being upset into a wedding band. It's a nickel white gold, and you can clearly see that through that deformation process, we're getting uneven deformation. We tend to get more deformation at the surface than we do in the centre, and when we start to recrystallize, which is what the bottom right-hand picture is showing, you can get a variation in grain size because we had a variation in the amount of deformation in different parts of the crystal. So how do we use annealing to control grain size? It will depend on the amount of cold work that we put into the material before we anneal it. depends on the annealing temperature and it depends on the time of anneal. And generally, as rules of thumb, the more cold work we put in, the finer the grain size. If we anneal material that's not been worked very much, we will end up with a larger grain size. And if we anneal at too high a temperature, we'll also end up with a large grain size. And generally, be aware that there is a critical amount of cold work that you need to put into material before it will recrystallize. That typically is about 12 to 15% for the precious metals reduction in thickness. This is a very good illustration of the effect of temperature and time on the crystal structure of a 2N yellow 18-karat gold. The temperature is getting higher as we come downwards, and the time as we go out to the right is getting longer. You can see at the low times, low temperatures, we've got a fine grain size, top left-hand side, and as we come down to the bottom right-hand side, higher temperatures, longer times, we're getting quite large grain sizes. So just by controlling the time and the temperature, we can have an influence on the recrystallized grain size. So that's an important way of controlling. The problem, of course, is if you're torch annealing, you have got much less control. The tendency is you overheat and you end up with a large grain size. And as I said earlier, if you've got uneven deformation within your structure, you'll end up with an uneven recrystallized grain size. And this is an example, again, of an 18-karat nickel white gold C-shaped wire. And we can see on the inside, we've got a much finer grain size than we've got on the outside. This may or may not be important, depending on what subsequently you're going to do to make your piece of jewellery. This is just a schematic of what happens when we increase temperature from a cold work structure, and you will see about halfway along the dotted vertical line, that's the temperature at which recrystallization will start. Our hardness starts to drop, but you see if you watch the green line, that's our recrystallized grain size. The higher the temperature, the larger the grain size is going to get. So we need to control the way we anneal our materials. And as we've said, one of the downsides of a large grain size is if you're doing further working, you will end up with an orange peel surface, and that's often a problem if you're torch annealing. If you've got a two-phase alloy, tends to lead to a higher deformation within the grains and tends to lead to a finer grain size on annealing. But if you've got very, very fine, even distribution of second phases, it can, if you get too fine and too close together, start to inhibit the recrystallization process, and you may find you need to use a higher annealing temperature to compensate. So it's not always an easy path to navigate. Lastly, I'm going to talk about grain refiners, just quickly. Grain refiners are very small additions, typically less than 0.1%, that we add as a very fine powder or as perhaps tied up in a master alloy, for example, to carat gold, but we can do it with silver and platinum and palladium to promote a finer grain size than we would otherwise get. If we are looking at getting a finer grain size in casting, traditionally we've used iridium or ruthenium, and they're very effective in giving us a fine grain size. If we are looking at refining the grain size during recrystallization annealing, then we will probably use a little bit of cobalt. Both work by promoting enhanced nucleation during solidification or enhanced nucleation during the recrystallization process. If we don't do it well, particularly with iridium or ruthenium, they tend to be heavier than the gold that we put it in, and they will sink to the bottom of the ingot, and you'll end up with nests of hard particles on the surface of your ingot, and as you roll it down and polish your final jewellery, you'll find you've got all these comet tails on the surface that you can't polish out. But not only do we use these materials, there are a lot of other elements that we traditionally will use to refine grain size: boron, beryllium, yttrium and the rare earth metals, rhenium, rhodium, nickel, barium, zirconium, all of these are used depending on the alloys and the precious metals to refine our grain size. And in a recent a patent that I was looking at not that long ago by a certain company that's got something to do with JTF, but I won't mention their name, they're using a combination of elements because they believe that's more effective at refining the grain size. So I just give you some examples of the use of grain refiners here. The top two pictures is an 18 karat yellow gold. On the left-hand side, we've used iridium as a grain refiner. On the right-hand side, we haven't used any iridium. And as you can see, there's quite a marked difference in the grain size there. On the bottom, we've got a 14 karat yellow gold. On the left, we've used cobalt as a grain refiner during recrystallization, and on the right, without. Again, I think you can see quite a marked effect. If you're using cobalt, you need to bear in mind from a practical point of view that you will often add the cobalt as a copper-cobalt master alloy. There is a limited solubility of cobalt. It will depend on the silver or the silver-copper content. So that may limit the amount you can actually get into your melt. And lastly, I'm sure you're all pleased to know we've come to the conclusion. So just a general summary. Generally in jewellery, it's desirable to have a fine, small grain size in jewellery alloys. Coarse grain sizes lead to the orange peel surface problems, enhance the tendency for cracking, reduces our strength and hardness, and also reduces the ductility of the alloy. We've looked briefly at the influence of casting conditions on the grain size that we get from the as-cast microstructure, and the influence of the conditions of casting in terms of nucleation of embryonic crystals and the solidification patterns. We can use that to help enhance our fine grain size. And we've also looked briefly at the deformation, the cold work we put into our material and subsequent annealing, and how the conditions we do that under also influence the recrystallized grain size. So as we've seen in annealing, the temperature at which we anneal is important, and more important than the time. High temperatures lead to grain growth, and that can be undesirable. And we've also lastly finished off by talking briefly again about the use of grain refiners, whether in solidification or in recrystallization, to promote a much finer grain size. And I know a lot of people, commercial alloy producers, will use grain refiners to ensure they get a finer grain size. So that's all I want to say. So thank you all very much. And I'll just give you one more example. And this is from Australia, 18 karat yellow gold, large tubes using iridium. And we've got two levels of iridium in the middle and on the right-hand side. And I think you can see quite clearly the effect, again, of grain size by the use of grain refiners. So thank you all very much. And I'm done.